Here the recording has started. I could notice, just to inform everyone that we are recording the session. So I will hand it over to you, Lushan and Z.
Thank you very much. Hello, everyone, on the SAM session. So just once more quick update. We are about statistical analysis of the subjective scores, interested from choosing the best subjective metric from a subjective experiment to better understand how subjects do how they score within the subjective experiment, and finally also thinking about what we can do to better analyze the results, but also maybe better like perform subjective experiment itself to get more correct results, and then maybe statistical analysis can be easier or more straightforward. So all those topics are definitely within the interest. And as I said, the last year we focused on this MLE method that becomes standard, and this is definitely the biggest achievement from our group for now, but we are not stopping there. And at the end of the session, we will have discussion about the future of SAM, and we are really very, very waiting and welcoming any thoughts you have and what we can do there. Okay, but now we will start from presentations. I believe we're starting from Z presentation about a subjective experiment dataset. So please, the floor is yours.
Thanks, Lucian. Let me share my screen first. Can you see my screen?
Yes.
Yes.
Okay, let me get started.
Not yet. Yeah.
Okay, so good morning, good afternoon, and good evening. Today I'm going to be sharing our recent learnings by evaluating the CANBE algorithm. CANBE is Netflix's recent banding detection algorithm. The details of this detection algorithm will be presented on Tuesday's norm session. But for this presentation, we're going to be focusing on the story of two data sets. Let me get started. So just to give you a very brief introduction, banding is also known as force contouring. Basically, it's a force staircase-like edges in otherwise smooth transitions in a picture. And one of the most prominent courses for banding is quantization when we apply lossy video compression. And other significant factors that could affect the visibility of banding is the bit depth representation of the video signal. So in the most typical case, we use A bit, but like more high-end encoding uses 10-bit. And one of the major motivations is to eliminate this kind of artifacts. And just to give you some visual example, in this slide and the next one, I'm showing an example of 8-bit depth versus 10-bit of exactly the same shots from the same video content. I don't know how much visible you're going to be seeing because I'm presenting through the Microsoft video conferencing software, but I'll be making the slide deck available afterwards, and you will be able to look at those two slides and back and forth to compare the visual quality of them. And this is 10-bit. So over the process of developing CANBE, we have conducted two subjective tests to collect data to support mainly algorithm tuning and validation. And the first one is the CANBE 8-bit test, which uses only 8-bit encodes. And the second one is the 10-bit test dataset, including 10-bit encodes, but also a subset from the 8-bit encodes, which overlaps with the 8-bit test. can see it's represented in this Venn diagram. And for data analysis purposes, we use two techniques to calculate the MOS. The first one is bias subtracted MOS, which is standardized in ITU TP 913 section 12.4. And the second one is a bias subtracted consistency weighted MOS, which is recently standardized in ITU TP 913 section 12.6, but also in P910 Annex E, which is currently under pre-publish status. So one of the major interests why we're introducing this overlapped A-bit encodes between the two data sets is for us to hope to be able to calibrate across the two data sets such that we can aggregate results. And when we use these techniques to analyze the two data sets and compare the common data points, we put them into a scatter plot. On the left is using this the first method, bias subtracted MOS, and on the right is bias subtracted consistency weighted MOS, the second method. So we spot a few trends here already, right? The first trend we see is there's a systematic bias when we when we test the same encodes in the 10-bit test. You can see there's a systematic negative bias in here. And when we apply the second method, we can see this trend is even further. These are the two puzzles we're facing, just to summarize it here. The first puzzle is, why do the shared A-bit encodes receive lower scores in the can-be 10-bit set test than the can-be A-bit test? The second puzzle is, why does this analysis using the second method further encourage this behavior? So we start digging, and one of the first thing we look at is, let's inspect the entire can-be 10-bit data set. Previously, we have seen the ones that's only in the intersection, the A-bit, right? But let's look at the entire data set. And what's been shown in this slides is a scatter plot, right? So on the y-axis is what you have seen before, is the MOS score recovered by the first method, the bias subtracted MOS. And on the y-axis is the can-be score using the can-be detection algorithm. So just to give you a very high-level idea, how you can interpret the can-be scores. So here, 0 means there's no banding, right? Detected by this algorithm. And typically a value of 24 for can-be is pretty severe banding. You can think it as pretty unwatchable. But of course, it depends on the viewing condition. The darker the room, the banding is more visible, but 24 is pretty bad. And around 5 is where the banding starts to become slightly annoying. So when we put the data here, you can see they're in two different colors. The black one basically representing all the 10-bit encodes, and the A-bit encodes shared between the two data sets are represented in red. So you can see this is the typical recovery results by the first algorithm. So similarly, we can use the second method to do the recovery. And it also representing the scatter plot here. So if you compare them and making observations, so the first observation is the following, right? The perceptual quality of the 10-bit encodes in the can-be 10-bit test data is very concentrated in a small region. And we can see from what we know, this encourages stimulus spacing bias. That's typically the reason why in a subjective testing, we need to ensure a perceptual uniform distribution across different stimuli, the stimuli set. And because of that, so the stimulus spacing bias is basically how when viewer trying to evaluate the quality of the stimulus is trying to map more uniformly. If it is not uniform to begin with, to try to use the scale to its full extent and trying to distribute the scores more uniformly. And when it applies to this case, we can see the pure effects is when it comes down to the A-bit encodes, their scores got pushed down by these effects. And which is kind of explain why you see there's a negative bias when the A-bit encodes has been evaluated in a 10-bit data set. And the second observation is the following. The pure effect of having this consistent weighting, which is the part that the second analysis method has, but the first doesn't have, is that it brings up the 10-bit encode scores and bring down the 8-bit encode score. And very interestingly, coincidentally or not, the correlation between the MOS and the Canby score also improves. So the question is, how does consistent weighting manage to achieve this effort? So as we dig deeper into this, we look at more visualization. What we found is this is actually accomplished by the method being given unequal weights proportional to the subject's consistency. So you can see from this visual example on the upper graph, it basically shows the raw scores in presenting a two-dimensional matrix with the color representing the different scores. Just by inspecting the scores, you can see there are 3 subjects, number 3, number 4, and number 5, produce scores of quite large variability. They're very inconsistent with the rest of the scores. And this can be considered as a very high random error. And this effect leads to regression to the mean in the overall score that has been recovered, especially when you're using the first method. When you use the second method, this part of this consistent weighting will give less weight to these 3 subjects. And this, as end result, reduce this effect as what we have seen in the previous slide. So based on observation, we made a few, there are a few lessons we learned from this study. The first is some of the subject tests inevitably have perceptually unbalanced stimuli set. This could result in stimulus spacing bias and introduce systematic error and random error to the data set. The second learning we have here is applying data analysis techniques like P913 section 12.6 or the same as P910 LXE could mitigate the random error introduced by weighting subject by their consistency, the so-called soft rejection. And the last one we have seen here is because these techniques adjust the scores only locally, and it doesn't help to address this global bias issue. It could not eliminate this systematic error. And that's the end of this presentation. With that, I'm open for questions.
I see a question. Oh, a lot of questions. Let me try. Unfortunately, I cannot see who was first, but let's start from Werner.
Yeah, thank you. So actually, the order is in the order that people have raised their hands, so you can just go top to bottom. So thank you, Steve, for the presentation. Yeah, it's always interesting to see these kinds of design problems that you only realize later when you have all the subjective scores. I wonder, like from your perspective, from designing the experiment, do you think that like looking at the stimuli again you maybe could have caught this problem and rebalanced the data set, or do you think you would have still needed the subjective test to see that error? Just wonder what the lessons learned are for you here.
Right. So what I see here, first of all, I totally agree that there's, for all the subjective experiment I did so far, for every single one of them, there's always something that you regret, right? There's always something that you wish you could do better to begin with. But so you just have to live with it because the data has already been there. And what you can do better is potentially try to clean up the data by through data analysis, like post test data analysis, that in hoping that the quality of the data could improve. I think both are important, the design, but also the post processing. And for this particular one, actually, my thinking is this. Sometimes this kind of bias cannot be completely eliminated because of the nature of the experiment, right? Thinking about, in this case, we want to evaluate what will be the effects of the accuracy of the CAN-B algorithm on 10-bit encodes, right? By nature, it is, it's going to be very challenging, right? Because 10 bits by nature doesn't have that much of a bending, right? So you already know that you're going to be having a set, a large proportion of those stimuli that's going to be not very visible in this kind of artifacts, right? So by nature, this experiment already have a quite imbalanced data, right? And I mean, this is inevitable, right? You might end up with in this kind of scenario, right? When that happens, I think the tool that you can have is by having a better post-processing analysis that could help you. That's my 2 cents.
Thank you very much. So Margaret is next.
Okay, very interesting. Thank you for this analysis. What you've been talking about, though, also makes me interested in the original purpose of these CAN-B data sets. Is there a paper that we can read? And if so, could you add a link to that paper to the meeting minutes?
Absolutely. Actually, Lukasz is going to be presenting the more details about this CAN-B, and you will see more about this tomorrow.
Perfect. Thank you.
Thank you very much. And Nabajit, please.
Yeah, hi. Thank you, Xi, for a very nice presentation. I just have a quick question regarding the playback. So when you play the 8-bit content along with 10-bit, how do you play that? I mean,
well, I mean, it's embedded. The information is in the encoded bitstream itself, right? You just need a player that supports it and a display that supports it. What we found is there are certain display that can support n-bit playback, like latest generation of the Apple Retina display. But the player also matters. Even if you're on a good display. For example, we found if you use the MPV player, you would authentically reproduce the 10-bit experience. But if you're on a VLC player, it seems to be converting to 8-bit. So you really need to be careful about that.
So you play the 8-bit exactly as 8-bit, right? You don't upscale it to 10-bit when displaying on the device.
You mean what's happening down in the pipe within the display? Well, yeah, I mean, each of the stage in the video playback pipeline is a bottleneck, right? You basically need to ensure every single stage is faithfully reproducing 10 bits.
Does it answer your question?
I think, yeah. I will discuss with Xi later, probably.
Okay.
Sure. Yeah.
Thank you.
Let's take that.
Thank you. Ioannis, please.
Yes, thank you, Z, and thank you, Lucian. And I'm taking the opportunity to also thank my co-chairs. I missed the very first like 2-3 minutes of your presentation, Z, and I will probably be missing more, but it's always good to listen to the great work that you and the team is doing. One of the important lessons that I can gather from this presentation is to make sure you have reasonable spacing in your stimuli, right? So the coverage should not just be, do I have the mean and do I have the max, but do I have a reasonably good anticipated ratings? And here is now the chicken and egg problem, right? So you, and I'm thinking out loud here, but my gut feeling here is that when selecting those stimuli, do you believe that either a pre-test is good enough, or even in the pre-test there's going to be this like spacing happening? So in other words, no matter what you present, is like you will always be seeing sort of a uniform distribution, even though this is not necessarily the case? Or should we, for this reason, and for this reason only, trust objective metrics to guide us which stimuli to select?
Right. Yeah, I would say definitely use the objective metrics as the first guardrail that you have, right? Because it's compared to the like even doing a pre-test, it's quite expensive in terms of human labor, right? The objective metric will be much cheaper compared to that. So always try to use that as a first guardrail. But sometimes the objective metrics is not very accurate for certain kind of scenario, right? Especially when you're trying to do an experiment to try to improve that objective metric, right? You try to find corner cases.
New use cases. Yeah, you're absolutely right. Yeah.
In that sense, I think you will be having to rely on a small scale pre-test in order to gather a limited amount of data. And seeing from there, I think it will give you about 80, maybe 70% of the information about what to expect, right? And if you need to make adjustment to that.
Right. Again, thank you.
Thank you. And this would be so beautiful if we have enough good data analysis that we understand what to do with unbalanced data. But definitely we are not yet there. Pablo, please.
Yeah. So could you go back to any of the distribution of the data? Because I'm trying to get a bit more understanding of the problem. So basically, you have one. So you have two different tests. One just with the 8-bit sequences. These red ones and probably other ones, and the second one with those 10 and 8-bit sequences. Right? Is this correct?
So showing here is for the entire 10-bit data set. So I haven't visualized any of the 8-bit because the 8-bit data set is pretty, the behavior is pretty good. It's pretty benign. So I didn't show in here. So what's showing in here is all the points for the 10-bit data sets, but some of them are 8-bits, which also overlaps with a subset within the 8-bit data set. Does it make sense?
Yeah, I think so. So yeah, so basically you have at least the issue that these red points are probably rated lower in this experiment than they were rated in the 8-bit only dataset, right?
Yes.
Is this correct?
Yeah, I can go back to this one. That would be more obvious, right?
Yeah, but this is somehow. I mean, if you put if your 10-bit artifacts are your 10-bit sequences are better than the 8-bit in general, then this is kind of expected. I mean, if you mix, because people will tend to cover the full scale anyway. So if you put, people will always score in the context of what you give them. So if you create a new data set with a different range of quality, then definitely some of the sequences are going to be moved down. So this is for me, it looks similar to what the audio, I mean the speech people did when calibrating the wideband. So there's we all come from the speech because they're the first guys who did this kind of test were the speech people in the 60s and so on, and they developed a model for the telephony. I mean, very complex models and so on for telephony, and then like 10 or 15 years ago, they had to add the wideband telephony, the one codecs on together with the previous result that they have with narrowband, and it was a similar problem to that. They added new sequences, and then somehow the scores that were good in the context of narrowband speech, in the context of wideband speech, they were not so good. So this is kind of more or less what you would expect to happen. I mean, the scale of your experiment is probably going to be around the range of stimuli that you give to the people, and maybe what we need is a way to map them towards kind of an abstract scale that where you can do this kind of score manipulation independently of the range of the specific experiment that you have. I don't know if that makes sense, but this is somehow what we are searching, I guess. But this I don't think that you can kind of solve it in the design of the experiment, because you have two different data sets and they're going to be different by definition. I don't think you cannot force your people to vote the same way your 8-bit sequences in both experiments. I don't think that that's possible. It's more a matter of how to post-process the results afterwards in a way that makes sense and that allow you to compare between both experiments, which is a tricky question, I think.
Yeah, I just want to second what you said. First of all, I think the example I give here is a kind of special case, right? Involves two data sets, and in this particular case, inevitably you will have to have a imbalanced data sets. But in generally, I think we all should be checking our balance of the data set even before we do an experiment, right? So you can easily end up in that situation by not choosing the stimuli, the condition carefully enough. And this is actually quite common and generally being shared across video, speech, audio, right? The citation I had here is actually for audio. Ziniksky, I think it's very well-read paper, but unfortunately we never have a paper similar to that in the video community. But largely, I think those phenomena can be shared across. So I would encourage everyone also like a little bit more understanding about the adjacent field. So related to that, actually, I have this question. So in audio, how they counter this effect is, for example, they have something very similar to the video. We have Sandvik, right? In the audio community, they have Mushra testing methodology. In that methodology, what they do is usually introduce, besides the stimuli of your interest, they also introduce this mid anchor and low anchor, which is two different low pass filtered signal, right? Then using them as a lower anchor to calibrate the expectation from the user. But in Sandvik, we never have that. We only have a high anchor, which is the explicit or hidden reference, right? But we never have something like a low anchor or mid anchor. I'm wondering from the audience, do you know the reason why we're not having done something similar to them?
If anyone could answer, then please just go ahead.
Lucian, I just want to make sure I'm doing an audio check. I'm switching to my phone, and I really apologize to the group if I'm sometimes going to be requesting priority to talk. I'm no longer in front of my computer, but the one quick comment I had, I don't have an answer to your question, Z, but back to Pablo's point, I think there is a little bit of a difference between what you just described on the audio side, Pablo, and what we're seeing from Z. One is when you have a set of stimuli and you are extending the upper end, right, by adding something that was, let's say, far superior to what people have seen on another test. And I think that's very well explainable. What I see here is that we already had on the 8-bit, I did notice some red points, if I remember correct, Z, correct me, on already, rated as 100, right? So it's really the spacing. You now have much higher density of, let's say, good content, is how I would like to call it. So I think besides the fact that sometimes in subjective experiments, you are extending either the high or the low end, here we're talking about density. And I believe that's the number one issue we are seeing. And again, my apologies if I'm sometimes going to be jumping without really knowing how does the queue work. Thank you.
Right, I think it's about the range that you cover plus the frequency, right? I think eventually everything boils down to the density, right? You want to like even density across the entire range, right? Not just about as long as you have the coverage. I think you need to make it uniformly distributed.
I still will stay with my way of seeing it. So I know that the easiest to analyze will be to have the uniform coverage of all the quality range and the also the uniform, like the density is uniform. But in my opinion, if we could understand subjective experiments better, maybe we could, because actually, in my opinion, what we see is an experiment that is somehow simulating 10 bits monitor is the one that we see, and 8-bit monitor is the other one. So on 10 bits monitor, I will see 10-bit content with a certain range of quality, probably mostly good one, and then 10 bits which can have much worse quality. From time to time, they are presented. And then if I have 8-bit monitor, I see only 8-bit, and then I have a full range. And my behavior, like as a user, I'm used to some distortions because I have 8-bit. If I have 10-bit, then I'm less used to some distortions because they simply appear rarely or not so often. And in my opinion, this would be really beautiful if somehow we could try to make one subjective experiment and conclude about both the type of monitors from one. For now, it's definitely impossible, and I think this is super difficult. But in my opinion, this would be really, really nice. Okay, sorry for jumping into the questions. But Lucas had a question.
Go ahead, please.
Yeah. Ooh, sorry for the sinister lighting. Too many points. Actually, a lot of great discussions. One thing I wanted to point out was about the relation to the audio and the anchoring. Actually, this seems that the anchoring will not really properly work the same way as we thought it might be, because this is exactly what we did in here. So the 8-bit test, just to give a little bit more context, was really prepared in a way that everything was really well spaced. Everything was covering very uniformly the whole scale, basically from not annoying banding to very annoying to unwatchable banding. Then we were facing this problem with the 10-bit test. So do we just have completely detached test that has only the 10 bits? So we would be like artificially stretching the scale in order to really make it like unwatchable, even though compared to the 8-bit test, these videos would be much better quality. Or what we decided to do was just stay with like include the worst case scenarios, the best case scenarios from the 8-bit and some things in between, and then add the 10-bit encodes inside of the data set. And this is exactly what it created. And I agree with Pablo, it's not really unexpected. This is something that we have seen. The thing here is more trying to analyze which method is better in order to recover the underlying real perceived quality scale. And yeah, I think we're still not there. We really need to figure out how we can use, for example, data points we have in between of the two data sets in order to map them together and so on. But yeah, just wanted to point out this distinction, and also, yeah, showing that virtually from two different data sets, even though you really fix the range and everything, you have very similar conditions. These effects will always be in play, and we really cannot really map two data sets so easily to each other as we may have thought before.
Thank you very much. I think we should coming to the end with the questions to this presentation. We have another one. I see Irena.
Yes, hi. Well, part of my question was actually answered, I think, by Lucas. I was wondering how the stimuli from the 8-bit encodes were selected, like the overlap set. was selected, because I guess that selecting some samples that are uniformly taken from the entire range, so taking some that are from the very low range of the Cambi score and some from the very high range would lead to this plot, while maybe selecting some contents from the 8-bit encodes that are still on the higher end, so they would be only on the in a range that would be similar to the 10-bit encodes, then would stretch the scale, as you mentioned. And I wondered how you solved the thing, but I think you answered to me. And another question that I had was about the training, if any training was done to the subjects, and how was it done? Was it done on both the 10 and the 8-bit encodes? Was it done only on the 8-bit encodes? Because that can also influence the range of the scores.
Lukasz, do you want to address that?
Sure. Yeah, so the training was the same for the two data set, and it was only 8-bit encodes. So again, we did as much as we could in order to keep the range and scale that people are introduced to the same within the two data set.
Okay, thank you. Yeah, I think that this could influence a bit. It would be interesting to see what happens when the 8-bit subset is from the higher end. But I guess that then you have the scaling artifact.
Okay,
hear me?
thank you.
I'm not sure if my audio can get through.
Yes, we can hear you very clearly.
Oh, again, my apologies. I just wanted to make a quick point on what Lucas just mentioned. So, Lucas, I think what are concluding here is that actual people, forget about subjective tests, right? I'm talking about an actual viewer. An actual viewer who's going to watch a mix between 8 and 10-bit encodes is going to form a different opinion of how good or bad they are compared to the same person if he or she was only showing a set of 8-bit encodes. Similar to, you can extend that to maybe somebody who was watching HD versus 4K on a 4K monitor, and for as long as he or she is watching HD, has a different opinion about what they are watching. So I'm not really sure whether there is any actual need to quote-unquote normalize or simply accept the fact that humans are conditioned and form opinions based on what they are exposed to. So I think there is, the more I reflect about it, there is nothing really abnormal, and this all makes perfect sense to me. Thank you again.
Yeah, so this is something that I also pointed out, and I fully agree with that. That those users are different because they have different equipment. Okay, Margaret.
Okay, I want to give an answer to Z's question to us about comparing audio testing with video testing and pinning the upper and lower end. Really, I don't think you can easily compare the video testing to the audio testing. Audio testing is usually speech quality testing or speech intelligibility testing. There's a fairly well-defined range of quality, and it hasn't really changed that much over the past 30 years because the systems were much more mature 30 years ago than video. And if you just look at the quality levels, they haven't changed that much. Now, if you look, the interesting range of video quality has changed enormously over the past 30 years. And there's a very broad range of impairments that are mapped to bad quality. So because of those two reasons, I just don't think you can have the same solutions.
Right, Marcus, so basically you're saying on the video part, we're more like having a moving target, right? That's keep on evolving. It's difficult to, got you.
Yes, yeah. Two problems. The moving target is an enormous part of it, but the widespread of very different levels objectively we can call quality mapped to a single subjective, this is bad. That's the second problem.
Right, yeah. It's hard to define what bad is, right?
Yeah, yeah.
Thank you very much. Yeah, this is interesting. In my opinion, for me, it's super interesting topic to discuss, but probably not for this meeting, somehow in the future, about, the training and how much we should or we shouldn't train subjects. All right. Anyway, this is the end of our discussion, super interesting discussion. Now we can move to Pablo's presentation. Pablo, the floor is yours.
Thank you. So let me share the presentation, if I'm able to. So this presentation is a follow-up on the 4 subjective experiments with 4 subjects, the 4 methodology that actually Lucian presented in the last meeting because I wasn't able to. So now I come back and to do my job. I'll recap a bit on when we presented last time and some follow-up on what we have been thinking about this. So what is this whole thing about? And yeah, I'm not going into the details because they were already presented and they're in the paper as well. So the starting point for us when we start discussing this experiment is the subject model that's been discussed and reworked a lot by Sam in the last years, which is that you could model the subject score as a random process. You could have subjects giving you like a true score and subject bias and some inconsistency due to the subjects and to the PVSs themselves. And in the original paper, there was this idea that a few subjects, 8 subjects with 3 repetitions, behaved similar to 24 unique users. And this was part of the idea of building this model that should be stable across the same subject doing a repetition of the same experiment. So the idea was, okay, what if that was really true? And you know, if you put a subject to score once and again the same experiment, you could expect that this random variable of this subject converge to the true quality that you're looking for plus a bias. And then if you could also remove that bias, maybe even after enough repetition, a single subject, I mean, even your own, should converge to the ground truth. And then you don't need to recruit people for experiments anymore. You just put yourself a lot of times in front of the screen and you rate your own content, which would be very nice. And we did an experiment trying to validate that or to understand that, which is already published in early access and IEEE Transactions to Multimedia. So we built a data set with a subset of the ITS4S sequences, then the 100 Everglades sequences plus 10 from a different subset of the ITS4S sequences. And we recruit subjects to perform the same experiment, so to replicate this ITS4S experiment 10 times. We recruited 27, and 20 of them actually completed the 10 repetitions. And we somehow wanted to compare this new data set with the original one, based on a number on a set of different scores that we thought about and extensively discussed in the paper, including association agreement, some perceptual similarity metric, and the confusion analysis framework that Margaret has presented a couple of times here, I think. So the results are again in the paper and were already presented in June. So I will not go into them, more directly to the conclusions. And the conclusions were that okay, you cannot get the real scores from a single subject. But a few of them, even experts, repeating the same experiment in different days could make more or less the job. And the conclusions from the study was that 4 subjects doing 4 repetitions could get you like a 15-like subject experiment, and 6 people doing 5 repetitions could make you something similar to a standard 24 subjective experiment. So we've called this a quasi-experimental methodology in an analog sense, as quasi-experiments are thought in other statistics situations, which is okay, a situation where you somehow cannot have fully random population when you run the experiment, but you have some control and a way to control that absence of randomness, which in our case is making people repeat the experiment several times. And it's something that we thought could be an interesting methodology for situations where you cannot have a large number of subjects, but you still want to have some scores that are much better than just a small pretest or an objective metric because maybe you don't have an objective metric for the quality type that you are assessing. So far, what has already been presented, I tested this methodology together with some other colleagues to get some results, evaluating some algorithms that we were working on in our research team. Because again, we were not able to have, due to COVID situation and so on, we were not able to produce a standard subjective evaluation for them. So what we wanted to do was, in this particular experiment, compare perceptual performance of semantic segmentation algorithm compared to the typical algorithmic performance, which is the intersection over union, among other metrics. So this is, it's also been presented in this conference in IEEE-AI VR a couple of months ago. And you can find the details, or I can send you the paper if you are interested in the details. Basically, what we have are some algorithms that are able to segment your arms or your feet from a full image. And then we have some people evaluate this segmentation across either a black background or some kind of other types of backgrounds that were significant to our problem, because we are using this to actually introduce your own hands or legs within a VR experience, basically. So this is the bottom line of the whole thing. And okay, at least it has served us to compare the perceptual versus the algorithm performance of the semantic segmentation, and to be able to select. So this top row is the result of the perceptual test. The bottom row is the algorithmic are the algorithmic scores. So it has allowed us a bit to complement the results from the algorithms and see that some methods that maybe according to the algorithms apparently work better than perceptually do not. So it has allowed us to progress in the selection of the algorithms that we are using for our research and for developing our system. And of course, we plan to complete that with a larger test with other subjects to verify to contrast the results. But at least, okay, it gives an idea that this can work. It can give you significant results, and those results could help you in the development of your application, which is basically the main target of developing this for methodology, this for us, because sometimes you need to keep progressing on your work and need a way to quickly evaluate your intermediate results without going to the expensive process of running a more formal test. So far, so good. And these are basically the next steps that we are planning. Not just me, also the rest of the co-authors. I mean, Lucian and Margaret and Narciso, because this is a joint work between us four and our labs. So on the research side, of course, we want to perform more experiments to test the methodology and its properties. And also we are already planning to do further analysis of the existing database, because we have, it took us a lot of time to obtain this data, and we still think that there are more information that we can extract from having 20 people repeating the same experiment 10 times. But we also think that this kind of methodology is useful for people who are in the same situation that we are, that I was, let's say, when doing this research that I presented you the previous 2 slides, which is okay, not being able to have 16 or 24 subjects to run a subjective test, and therefore you need to do something else. And we are thinking on proposing this methodology to ITUT, particularly for this kind of test. I mean, for pre-tests or for expert assessment. Sometimes you don't have access to 24 experts on the subject matter that you are evaluating. So maybe you could have more scores by having them repeating the experiment a couple of times or 4 times, or any other kind of resource limitation like time or funds, or including this pandemic situation where having different people in your lab is difficult. So this is the rationale, and basically what we are proposing are the 2 baseline combinations that came from our paper. So basically, like a rough analysis, let's say, something similar to 15 subjects, so something good for correlation, not so much for actual agreements or for actual scores, let's say, which would be 4 subjects 4 times, and something closer to a standard 24 subject, which would be 6 subjects 5 times, all in different days, which is how we addressed the not having a very strong memory effect in the experiment. So this is what I wanted to present. I mean, this is a follow-up of the previous research. Of course, if there's any questions, feel free to ask. And if there's any comment or suggestion on the methodology itself or on our planned contribution to ITUT, that would also be very good to know.
So I don't see any question yet, I guess. And I just wanted also to add to Lodik that actually this is a perfect data set probably for your analysis of the or the best you can get because you have repeated scores from the same subjects. So you can kind of try to guess the distribution. Of course, just 10 answers is probably not super detailed distribution analysis, but still it's something. Okay, I see a question from Z, please.
Hi, Pablo. Thanks for the discussion. So from the last time, the presentation, so I went back to think about this methodology on a very high level, right? I think if you think about the random error that could happen in our subdata experiment, you can further divide that into effects. Just from a conceptual level, you have things like personal taste, right? Or the influence coming from your childhood upbringing, right? Or on the other hand, you have something like your mood, right? Some judgment could be based on like you do this test in the morning or in the afternoon. So if you think about those 2 kinds of error that could be introduced, both they are belonging to this random error, but so using this methodology by having that person to repeat multiple times, I think you can counteract with the second type, which is like more on your moods, right? You basically voted on different day, but if it's your personal taste, right, you could be repeating the same pattern, right, from a single person. I'm wondering whether you have any thoughts about how much effects that the first factor would have, and is there any thinking on how to counterbalance that?
I have some, and I have like a mixed, and it's something that probably would need to be, let's say, further studied a bit. But what we saw in the original experiments is that people tend to actually vote quite differently from especially in the first 3-4 repetitions from one day to the other. So of course not completely different, but I would say that the main source of error from a subject is this one the mood, which is not only the mood, it's also the fact that people need to decide between 3 and 4, and maybe one day they decide 3, and maybe another day they decide 4 so they can change their mind. It's not only the mood. It's also that they somehow need to give you a realization of their opinion in the scale that you give to them. And for a number of sequences, people kind of remember what they scored and they score the same all the days. But this happens just for a few. I mean, just about for. I don't remember exactly the proportion, but something between 10 and 20% of the sequences. So if your experiment is balanced enough and so on, it could be let's say it could be good enough. Of course, there's also this balance of a single subject, so which is basically the main reason why you cannot have one subject scoring the same thing a lot of times. In the experiment, in our lab experiment for the segmentation things, I have 4 subjects, and they have different biases, which are, so they have a consistent bias across the comparing one to the other. I haven't done the statistic. It's difficult to quantify because there are just 4 people, so it's difficult to be completely sure statistically. But if you look at the data, yeah, this happens, and this is what you try to address by having a few subjects. Of course, it's and there's a balance, and this is why there's a balance between the number of subjects that you get and the actual so the joint bias that you have. So basically, but the thing is that normally this global bias that one person has is kind of, I wouldn't say additive, but it's more or less that it will make you have some systematic errors on the exact rating that you get from this course, but it's not going to be so influential in the relative errors of your scale. So maybe and up to some point, it is the absolute level of error is something which is very difficult to get, because even if you, as you said before, even if you put a couple of even you have a lot of subjects, but if you shuffle the sequences that you have, and if you happen to put some of them which are concentrated in a range of the scale, then their whole the whole distribution of scores changes completely. So of course there's a limit on the precision that you can get in terms of the actual scores, but it's probably good enough in terms of comparing one HRC with another and seeing which one is better, which one is worse, which is normally what you intend to do with this kind of methods. I don't know if I have answered. So
thank you. Yeah.
Okay, Margaret, please.
Hi, so I would like to give an answer to Z's question from a different perspective. As researchers, certainly we're concerned about the differences you were talking about, Z, about one subject having very different opinions about the ordering of quality than another subject. The analysis that I did with Lucian data sets and ones I've done since, for example, the ITS4S2 data set had 12 different sessions, each with a different type of content. And in these analyses, we've not observed nearly as many problems with this sort of between subject genuine differences of opinion. That is, factors we can't explain with just random error. It just seems to be less of a factor in the tests than it is a concern with the experimenters. So although I don't think the 4 method is as valid as correct as actually doing 16 to 24 subjects, my opinion is it's certainly a good choice for the situations that Pablo pointed out, where you can't do 16 to 24 subjects. You can trust that these results are fairly close to what you would get. Thank you.
Thank you very much. And Werner, please.
Thanks. Yeah, I want to share some maybe anecdotal evidence that's not really properly verified, but we did have one test a while ago that was I would say a bit more ecologically valid than just a classical video quality compression test, because it involved stalling and rebuffering and different combinations of that with different resolutions of video. And so one part of that test was checking preferences for longer initial loading time and good video quality at the beginning versus shorter initial loading time and like a quality ramp up in the beginning, which people might have different opinions on. And what we saw in the results was that you could basically split the data set into two sets of subjects, and both of these groups had very different preferences here. So you could see that the ratings were favorable for both of these HRCs, depending on which subject you picked. And I guess this is something that if you had only few subjects, you wouldn't be able to really see, because it's such an individual factor. But then again, this probably only comes into play for experiments that really go more into this real application QE domain, and certainly it's not something you need to consider for pretest or anything. Yeah, just thought I'd share this.
Yeah, I totally agree. I mean, what you're describing is basically a test where you have two completely different factors, and you need people to actually balance the way that they give to completely different dimensions of the quality. And yeah, for that, I would not go with this methodology because I think that's is going to be, once you have two dimensions, you probably need to, maybe there's an alternative or alternative way to do this kind of things of pretest for that, but it's definitely going to be a bit risky. In this case, we're more thinking of a single dimension, meaning, of course, you could put different kinds of impairments because there were different kinds of impairments. We have like frame rate impairments or bit rate, compression impairments, so not just a single source of them, but more or less, things coming from the same dimension of the visual quality. The experiment that you describe is more complex, and probably I would not. You should understand a bit this framework of how to mix the two sources of quality impairment before being able to design this. Yeah.
Thank you very much for the comment. And Naeem is.
Yes, actually. Thank you very much. Actually, it's a very interesting topic. I would like to give my input with respect to this one, because we run this test, but it's in a different context, especially for the physiological signal wise, but it is about the subject identification. And we run the test in a different weeks, actually. So one subject comes in this particular week, and then he has to come the same day next week to us. So in this one, because it's a physiological signals, and then we would like to see that one, how the emotions actually work with respect to the different weeks to the people, because everyone has some background emotions as well when they are coming and joining our any session, right? Either it's a video quality or in other contexts we are presenting to them. So how we have to be, because this is another dimension we have to be add in the test as well, that the pre-conditions of the subject as well, that either, for example, in this study, we have some emotional changes. We identify that one. For example, when the people they are in the happy mood and all these things, then we saw that when their rating is little bit more relaxed as compared to when they are some tense situation like exam is going on and all these things, then they are very reluctant to give the a very high marks of the sum of the content. So this is the one of the dimension, because definitely this is a physiological study. I'm not talking about, but I'm thinking that this is one of the dimensions you have to be considered as well while doing this in a different days for the same subject, this type of test. And another point of view as well, that when we have a very small subject number, right? So and out if we have a large number of subjects, then that's mean the outlier we can easily remove, still are tested valid and everything is going on. But in a small scale study subjects, then if let's suppose one is an outlier, then that's mean you have to be redo the test again. So this is another see that. But anyway, overall it is a good. So if I would like to see a little bit more results on this one, and then we will see how things are going.
Thank you very much
Yanni.
for this point.
Yeah, thank you. We have some, so concerning the outliers, of course, you can never know, but we have some people who were in the original experiment that we thought, because we knew them, that they were going to be really outliers in the way that they, think about quality. And anyway, we haven't found, the paper is published and so on. So you can look at the results. And due to the variability of having some people scoring a lot of times and so on, we haven't actually found anything extremely concerning. Of course, if the methodology is more used, then problems will start to arise and be analyzed. But as Margaret said, it's this kind of things is normally more a matter of what we think that's going to harm us as researchers, that what we actually get when we run the experiment. But of course, yeah, this may happen.
Okay, Loic, please.
Yeah, thank you, Lucian, for this very, I say Lucian, but also Pablo and all of you for this very interesting work. And I would like to know, as you mentioned it before, where I can find the data. This is my first question. And another one is, I think Z talked about the memory effect on this procedure. And I was just wondering, since you are the implicit assumption behind your analysis is that repetitions provided by the same observer could cover the variability that you will get basically in the data when using many observer. I was just wondering whether it is not interesting, for instance, to look at the time series of the values of inconsistency and bias of the same observers, to see whether the range of variation of these values really cover the typical range of variations that you see in the inconsistency and bias when you use many observers.
Answering to the first question, it's the data are in the CDVL library. I don't know if Margaret could put the link in the minutes, but
yes, I'll put the link in the minutes. This is on the Consumer Digital Video Library, and if you search for FOWR, you'll find it. But I'll add the link.
So yeah, look at the minutes and you will find the link. And yeah, the one of the further analysis that were planned was particularly that I think that you're suggesting, which is estimating the bias individually of bias and inconsistency of the subjects in each of the repetition, and see if the estimates using Surreal or whatever method is consistent on its own with what we see across time, which has a lot of it's quite tricky. Anyway, we've had a lot of discussions on that, and we're more than open to keep the discussion offline. But feel free to have a look at the data, Loic, and run whatever test you want on them, and contact us if you want to collaborate in further analysis.
Sure. Thank you, Pablo. I will do that.
Thank you for all the questions. So yeah, my just small comment is exactly what Pablo said. So in repeating or going back to Z question is, I would say that actually what we observed is that probably the personal taste bias was surprisingly for us not so much visible. And it seems that this momentary change is much stronger. And in my opinion, this is also coming back to what Werner said, that actually, because those experiments are not ecologically valid, so people really, at the end, they answer within the experiment, let's say, framework, but we don't see really very strong influence of personal taste on the results, because of, you know, the people really fit to the experiment instead of really expressing, let's say, themselves. Yeah, but this is a broader problem, also questionable what we want. It's not obvious. Yeah? But anyway, with this group, as we said, we would like to propose the method for the standardization, and for that, we would really love to see the results repeated by some other labs. So we can definitely help. By me, I mean all 4 people that were involved in the experiment for sure. But we would love to see someone who would like to repeat the experiment. So if you have any resources for that, it means you have some friends in the lab. And you don't like them so much that you can force them to repeat the same experiment like 6 times. So then please let us know. We would be very happy to try to do the repetition and then some comparison. For me, for example, this would be super interesting if more than one person, let's say, come to us, then we could try to do a comparison, like, because we can easily imagine that a very small subjective experiment will be much more, you know, destroyed by the memory effect comparing to a longer one. So then we could try to play with that as well. But anyway, if you have idea, you can join our effort to test this method further. It would be very helpful. Okay.
Lucian, can you hear me now?
Yes.
Yes, sorry again, I was trying to intervene earlier to indicate I have some point. First of all, on the point that Werner brought up, that's a serious concern/issue that I would also like us to explore, which is, so far we are treating every single individual as an individual, right? So we accept that whatever bias, inconsistency is individualized. But have we even considered the fact that there can be clusterings of these subjects in the way that they perceive quality? And the example brought by Werner, I think, is a very valid one. I think I can definitely relate to it. There are definitely people who prefer a longer, you know, pre-buffering time and a better starting quality than someone who says, okay, let me start watching and then quality improve. And I would add one more, again, based on my experience, divergence of opinions that seems to be clustered. Those who prefer blocking artifacts and those who prefer blurring artifacts. So I think a meta-analysis perhaps could help us understand whether we can arbitrarily create, you know, cluster our observations and our observers actually into people that have some common trait. So that's, to me, a very interesting component that can help us understand not just what is the mean opinion score, right? Because if the mean opinion score means, you know, those who like, who are, you know, class A have this and those who are class B have B, it's best if we can present these 2 results as 2 separate numbers rather than try to force them into a single number. So that to me is very important aspect. And the second one I would like to comment is the one that was brought by Naeem. So I think we should really differentiate between short-term variability and long-term variability. There are multiple reasons to consider, at least in my opinion, that these are separate effects. and having the exact same subjects being, subjected to this torture of being done, in one session, have multiple ratings, versus the same subjects being brought back in 3 or 4 different weeks and ask them to repeat the same ratings, would reveal a lot of how much is A versus B. These are my 2 thoughts, and with that, back to you. Thank you.
Thank you very much. Yeah, it's very valid question. For me, the first problem you attack is how to make subjective experiments such that we can see difference between people, because we know that this difference exists. Is topic of the research I do within the project sponsored by Norway grants, and this is very, very large in line of my main interest right now. So definitely, if anyone got any thoughts about it, I would be very, very interested. Okay, thank you very much. I think we can close this discussion and go to the next presentation, which is done by Irena. So
yes.
The floor is yours.
Thank you. I will share my screen so that I can, and I think you're seeing my screen now. And I will start the slideshow, and I hope that it still works, that you can still see my screen and you can see my slides. So hello, everyone. This presentation is brought to you by me and Lucian. It was completed today, so please bear in mind in case you see any typos or any problems in the presentation. And it's an ongoing work that we've been doing about subject removal and subjective quality assessment, and basically analyzing how standardized methods work in this case. Now, the problem statement is the problem of outlier detection and subject removal. We know that people might not be precise in measuring the type of distortion that we want to measure. This can be brought, for example, by the inability of staying focused during the experiment. There can be some misunderstanding in the way that the rating is explained and then conducted by the subject. We want to detect this varying behavior in order to obtain precise conclusions. So we want to decrease the variability in the data. And one way to do that is to remove these answers that we think are random because the person was distracted, for example, or because they didn't understand the test in itself. But then the problem is how to define what is random, what is a person that didn't understand the question or didn't pay attention to the question at all, and what is something that is in line with the measurements that we want to obtain. And this brings us to the problem of outlier detection and subject removal of this thing. And in the literature, the most used methods for outlier detection and subject removal are standards. And in particular, here we're considering BT500, which is very widely used in order to detect outliers and remove them. It's based on some understanding on whether the users fit within a certain number of standard deviation within the mean of the scores that have been given. A more recent one is P913, and that considers the correlation between the scores that are given by one subject and the general population. And then there is the MLE method, which has been proposed very recently, that we're not considering here because it's not removing subjects, and we're really interested in the topic of removing subjects from the population, while MLE weights their contribution differently based on their distribution. Now, why did we start looking into this? We noticed that in several tests that we did, the BT500 and P913 were not reaching to the same conclusion in terms of the number of outliers, the outliers that were detected. And it got us wondering, how do they work, and are they really good at detecting any outliers? And to do so, we didn't rely on existing data sets because we don't have a really clear idea on whether the outliers that we see there are really outliers, or there are people that simply had a different opinion from the others. So we based our results on some simulations. And this is the simulation setups that we did. We considered 16 sources that were distorted by 2 distortion algorithms on 5 different distortion levels. So we get 160 PVSs. We consider 25 subjects and 100 repetition of the same test. So it's the same subject doing it 100 times, let's say. So there's going to be some variability within the subject rating. And you can see the plot of the type of simulation that we're doing, in which we show basically the distribution of the mean opinion score with respect to the distortion levels. We consider 2 scenarios. One is a typical test. The numbers were taken by, the paper that Lucian and Margaret wrote in 2015. But also, and I think that PVS standard deviation comes from a discussion within VQEG, but I'm not sure. Lucian will know more, in which you consider a bias with a standard deviation of 0.34 and the PVS standard deviation of 0.75 and an alpha of 10. But then we also wanted to see what happens when we have a super precise test in which there is not that much variability between subjects, and they're really the scores are really following a very tight distribution. And for that, we use a standard deviation of the bias of 0.01. For the PVSs, we need the standard deviation of at least 0.3. Otherwise, we see some bad effects coming from the discretization of the scores and an alpha of 100. And we test the 2 subject removal algorithms that are standardized in the literature, and we used the standard threshold that are defined in the 2 methods. And then we do some scrambling tests. So what we do is that for each repetition that we have, and we have 100 of them, we select one subject randomly. We first check that it is not an outlier, and if it is not an outlier, we scramble this its score, so the 160 score vector that is given to all of the PVSs, and we scramble it 1,000 times. And we want to check how many times this scrambling is correctly detected as an outlier, and also how it affects the distribution of the other outliers, meaning, is there any outlier that was there before and it's not detected anymore once we scramble this subject? And is there any new outliers that are coming out from this scrambling procedure? And first I'm going to show some results on the basic outlier detection before any scrambling. And we see that with the scenario 1, with the typical test, BT500 and P913 find a different distribution of outliers. We can see that subject number 24, in almost all of the repetition and in both tests, it's considered an outlier, and subject number 5 as well. But we can see that, for example, subject 20 is considered pretty consistently an outlier from P913, but BT500 is only detecting as an outlier once in the 100 repetitions that we do. So there is already some discrepancies without doing any scrambling in the test that we have conducted. And we can see that if we plot the sigma bias plot and we try to consider the probability of being detected as an outlier depending on the sigma and so the PVS sigma and the bias standard deviation value, we can see that for P913, there is some correlation to be found, especially between the PVS sigma and the probability of being detected as an outlier. We can see that the values become lighter, which expresses a higher probability of being detected as an outlier as the sigma grows bigger. While for BT500, we see that the probability of being detected as an outlier is generally low. It's around less than 0.4. And it doesn't show any real trend against bias or sigma. And then here we go to the results on the scrambling, which is the interesting part in our opinion. And we see that BT500 fails to detect the strangling 100% of the times. On average is between 80 and 90%. But we see that there are some cases in which the scrambling is detected less than 20% of the times. We also see that sometimes there are some cases in which the previous outliers, which are indicated in the yellow dots, are detected like maximum 80% of the times. The previous outlier is still detected after we scramble the data, but in some cases they're not detected anymore. So there's some outliers that completely disappear. And we also have a quite significant percentage in some cases of new outliers that appear after we scramble another subject, and then we just find that more outliers are popping up. Conversely, with P913, we see that the scrambling is detected 100% of the times. So we see that whenever we scramble one vector, it is always detected as an outlier. There's no new outliers that are detected after scrambling, so the scrambling does not affect the distribution of the other people. However, for previous outliers, and especially outliers that maybe were very close to the threshold, we can see that they're either detected or not. So it happens in some cases during the repetitions that previous outliers are not detected anymore, because probably the distribution of the scores changed, and then the threshold was, the value was slightly above the threshold, so that it didn't pass in the P913. Now, this was the scenario in which we had a typical test with a high standard deviation of PVSs. What happens when we have a super precise test is actually worse. We see that P913 doesn't detect any outlier, which is what we want, because we have a very precise distribution of scores, which means that the subjects are rating very closely to each other, and we don't expect any outliers. But what we witness is that in these cases, there were a significant number of repetitions for which BT500 completely broke. And what happened was that all of the subjects were detected as outliers. And these are all of the vertical white bands that you see here. In some cases, no outlier was detected. In other cases, roughly half of the subjects were detected as outliers. We cannot proceed in our scrambling test when all of the subjects are outliers, obviously, since then we cannot test any scrambling if everyone is detected as an outlier. So the plots here are less clean. Let's first check the sigma and the bias, and we see that there is no correlation between the sigma and the bias in both of them, but for P913 is because no outlier is detected regardless of sigma and bias. And for BT500, there's always a 70% chance of being detected as an outlier, which is coming from the fact that in many of the repetitions, all of them were detected as outliers. And what we see in the results is that the percentage of detected scramble is still not 100%, is much higher than before, so it's between 80 and 100%. In our case, the missing lines in the plot are the lines for which all of the subjects were detected as outliers, so we couldn't proceed with the test. No previous outlier was detected after we did the scrambling, and basically there was just a few number of new outliers that were added. Conversely, for P913, the yellow dots are null because there was no outlier before, so there is no outlier even after. 100% of the scrambling is detected, and no new outliers are detected after the scrambling. So our conclusion for this is that we do not recommend the BT500 method for outlier detection, because we saw a lot of issues when performing outlier detection, and especially we noticed that it failed to detect some very obvious tampering of the data. And also, in some cases for which we would expect no outliers, actually all of the subjects were considered as outliers. And I'm not sure how I would react personally if I had a test and then all of my data was discarded as outliers and I had to run it again. The P913 method seems to work fine for our test. We need to investigate the threshold because it's quite arbitrary. And in this case, it worked quite well, but we had the flipping that was due to the scrambling in the first scenario. And it needs further investigation when there's more variability, for example, between the subjects. And also for future work, we want to check different criteria for outliers that is beside the scrambling, because it's only one way of basically tampering with the data and getting random answers. So with that, I think that our presentation is done. So if you have any questions.
Yannis, please.
Thank you, Lucian, and thank you, Rene. I'm finally back to my desk, so I saw your nice presentation. I understand it's preliminary data, but my top-level question, and I may sound biased because I am biased. Even though it is a noble scope and a noble idea to find which ejection subject rejection method is better. I'm going back to, have you compared how would these results look? And I think the punchline is how mean opinion scores are affected, right? At the end of the day, why are we doing subject detection? Of course, we want to have a label to justify, and this is a curiosity, but when we're doing analysis, we are trying to see how our mean opinion scores are or are not affected, right, by doing proper or improper analysis. Have you compared how these results would look like in terms of the final score if we followed the MLE method? And most importantly, would the MLE just directly pick up the scrambled or the bad and by huge inconsistency?
Yeah, so this is definitely our future work. Yeah, this is something that we wanted to do from the beginning. Yeah, so focusing on MOSes. The beauty of simulation is that we know what is the true quality, and then we can see how well we extracted it depending on what we did. Did we use MLE and just weighted less as the scrambled subject? Or maybe it was better to remove a subject that is an outlier. If we remove subject, we lose some data, but we increase precision by removing the higher variance. Yeah. So this is definitely our first. This was our first thought, our first direction. The whole story here, pretty funny in my opinion, is that we just started from implementing the methods. We started from BT500. And wanted to test if our implementation is correct. And then we found out that actually scrambling doesn't really affect the method. And then we were like, well, we need to have an error because an outlier detection method which doesn't really show you that you had a problem with your setup and some results are completely scrambled. It's a pretty bad method, but it seems that actually this is the case. So yeah, this is definitely our target and the future work. It's not like we are completely omitting MLE because it doesn't remove subject. No, we are taking it into account because it doesn't remove subject, but it wasn't yet analyzed because we really stopped at this, and we just wanted to share our, let's say, discovery with the community to make people aware that actually it's really not a good idea to use this method to remove subjects. And we see it's pretty popular, yeah.
Yeah, but again, allow me to again. You as a co-author also and contributor, I think we made a very significant effort to change the mindset of the community and probably prove, or hopefully prove, that outlier detection is "quote unquote" old-fashioned. Right? I have nothing against exploring existing roads, but as a minimum, I'm very, very much eager and looking forward to perhaps showing that there is no issue if you use I hope that this is indeed the case, otherwise we still have a problem if you use MLE. So again, I understand this is preliminary, I totally respect, and I'm looking forward to the follow-up. Thank you.
Thank you very much. Jakub has a question.
Thank you for the very interesting talk. My question is about the sigma bias plot. Would you be so kind and explain to us in a little bit more details how these plots get created? Because I have a problem understanding what each data point means in this plot. Thank you.
Yeah, sure. So each data point in this case is one subject. And for each subject, we define a value of bias and a value of PVS sigma. So that's what we're plotting here, basically. So you can see that there's 25 points in here. And for each one of them, for each subject, we know how many times for BT500 that subject was detected as an outlier because we have 100 repetitions of this thing. So from that, we see, okay, out of this 100 repetitions, how many times that subject that had this particular sigma of PVS and this particular bias was detected as an outlier, and that influences the color here. So you can see that in general, like very few, I mean, like the outliers are the ones that I'm showing in this plot. And I mean, pretty consistently, as I said, 24 for BT500 and 5 were detected as outliers, but not more than half of the time, I would say. For P913, 20 and 24 were pretty consistently detected as outliers, and 5 in some of the cases. So that is the color that you see here, and probably these plots that you see in lighter color come from these subjects, which are detected a bit more frequently as outliers. And what we see is that for BT500, the color, first of all, it varies really between 0 and 0.4, more or less, because the probability of being detected as outlier is not that high, while it's higher for P913, because as I said, like, for example, I'm pretty sure that the 0.7 value, around 0.7 here, is coming from 20, probably, because it's the one that was more consistently detected as an outlier. We see that there is some sort of correlation with the PVS sigma, in the sense that as the sigma increases, the colors get progressively lighter, while for the bias, we don't see any such effect, basically, because they're basically distributed along the axis. Now, for the other scenario in which we have a super precise test, as I said, P913 didn't detect any outlier, which is the result that we expected, while BT500 sometimes was detecting everyone as an outlier. So that affects the percentage that you see here. That's why the outlier detection percentage for BT500 is around 70%, because it was really that some people were really detected more than half of the time as outliers. While for P913, sorry, it's always 0, the probability. So it is not influenced by the sigma or the bias, but it's because it's very, you can see this plot as the very beginning of the other plot, because the values of sigma and the values of bias are very small with respect to the other one. Does this clarify a bit?
Yes, thank you.
Thank you very much. Margaret, please.
Thank you for a very interesting analysis of the situation. Much appreciated. I have one comment and two questions. My comment is that I've never used the BT500 screening method. It always looked really odd to me. I just didn't trust it. So it was very interesting to see the analysis from that standpoint. My two questions, could you remind me what sigma is? And secondly, what ideas do you have for investigating the arbitrary threshold in P913? I agree, it's completely arbitrary. Thank you.
So for the sigma, I will just go back to the definition. So the bias is the sigma that we defined here. So basically is, but I think Lucian is more, because he implemented this part. So I think it's better for him, but they're coming from here, these numbers.
Yeah, so sigma is from the subject model, the standard deviation. We assume that the standard deviation, we are using the simplified model where the only standard deviation we have is coming from subject. So for each one subject, we pick a number that is a standard deviation of this particular person scores. And then each time we draw a score from this person, we use sigma to let's say, use the variability of those scores. So really higher sigma means higher variability of scores, no doubt. Then about the second question, well, this is much more tricky. Yeah? So if we want to use a different threshold, then probably our idea will be to focus on the statistics. Yeah, so like using a method of, if we use certain threshold, remove the answers from this person, do we increase our possibility of detecting statistical difference between different PVSs, for example, or not? And this would be the basic information. And exactly the same we can then compare to MLE as well, because from MLE we are not removing the whole subjects, we are just scoring lower the value for particular scores given by those who are less reliable. And then again, we can test the statistical difference between PVSs and see if we can kind of see more or less depending on the method we use. And for us, especially interesting is what happens for a different test. So let's say we are doing a test that is more difficult. We have subjects that have correlation or correlation between average subject and the overall mean drops to 0.7, for example, as an average correlation. Yeah, so not the this unique correlation, but the average just. So then obviously we expect that there will be some subject with very low correlation, like 0.5 or maybe even lower. And then if we use subject scoring method just using 0.75, then we almost removing everyone, which probably is not the something that we would like to do. So then again, for those cases, we would do the same analysis and hopefully get some decent answer or how to set up or how to detect which threshold you should use for your method. If the answer, of course, just coming to comment from Ioannis, is not that simply you shouldn't remove anyone and you should use MLE. This could be also an answer. Okay, thank you. And I guess that
really
Lucas.
Yeah, thank you. Thank you for the presentation. It actually really binds into what we have been looking into as part of MLE investigations. So we actually do have a data set that has 4 scrambled subjects, and 3 of them are detected by BT500. Different 3 are detected by P913, and it's never the 4 that actually are scrambled. So very much in line with what Yannis said. I'm a big promoter of an MLE method, because that one seems to be working much better on that particular data, at least, and on the data that we have seen. By a really interesting investigation. I'm just wondering about this whole, so bias versus sigma. What I have noticed is virtually you tend to be more likely to detect the subject as an outlier if the sigma is high and the bias is somewhere around 0. Because that's how the methods actually work. Like if the subject is scoring as well as the others in most of the times and then has higher variability, it detects this as a random behavior. Not sure if it's anything that is useful for the future work, but I think that's sort of expected and something that we can observe from the data as well.
I mean, I think that
probably need.
Sorry, go ahead.
I think we need much more simulations to know it, yeah, because we probably should make this plot nearly full, like drop the thousands of or 10,000s of pixels, and then if the square is more or less filled, then we could answer your question, but not with the super preliminary results.
Yeah. What I wanted to add here is that for BT500, for example, we do consider, like, the method does consider in a certain sense the bias, in the sense that there are 2 thresholds that are considered. And one of them is considering whether the subjects are outside of the standard deviations more than 5% of the times, and this is one threshold. But the other threshold is to see, okay, like the variation, the difference between them, this variation that happens, is it happening only on one side? So is it a bias that basically influences the subject to be always giving higher score or giving lower scores, or is it distributed around the 0? And when it's distributed around the 0, then the subject is rejected, while if it's between on one side or on the other side, it is not rejected. So this we see it is implemented within BT500. For P913, I guess that it might be influenced by the fact that we use the Pearson correlation, but I haven't given it a lot of thought, because it basically shifts the scale with respect to just stretching it. But
just to quickly jump back, is that's why I mentioned that the bias, in order to be detected, the bias should be somewhere around 0, because then it's actually, you know, the scores that are high variability ended up above and below. Plus, if there is a bias, then you will just discard this. Well, you will not discard this participant, because you say, well, they are biased, and then since they are biased, I don't really want to touch them. That's what BT500 does. When you remove the bias, then you can end up in the same situation. So that is just the way.
Indeed.
Thank you very much. You're perfectly right. There is a link between bias and variability. Okay, thank you. Dietmar, please.
Yes, thank you. My name is Dietmar Saupe from the University of Constance. Sorry, my video is not running right now, but I think I can speak to you anyway. So thank you very much for this interesting talk. I think outlier removal is very crucial for studies with subjective opinions, especially if you do crowdsourcing like what we have done in our group at the University of Constance many times. And I would like to bring, I don't share your negative view of BT500. We have used the spirit of BT500 quite successfully, I think. And you showed the formulas for the BT500 in one of your earlier slides, and or maybe you can go back to the formula. There it is, yes. So let me phrase it in words, what this means. And I think when you hear the meaning of it, then you will agree that it's a reasonable choice that they made. Namely, it means the following. There are two criteria in here jointly put together. The first one is that a person is likely to be an outlier in the subjective study if the mean absolute difference with respect to the consensus of the whole group is large. So, for example, if the overall MOS is 3 and the user scores all the time 5 or so, and does has a similar bias for many items in it, then it's likely to be an outlier. Another aspect is, or another criterion there in this BT500 standard is that in order to be an outlier, it is likely that, or outliers are likely to score inconsistently above and below the consensus, so above the MOS and below the MOS. So if there's a user who does like 100 ratings and 50 of them are above and 50 of them are below the consensus, then the likelihood of that being an outlier is larger. So BT500 combines the two in this formula that is shown there. If PI plus QI is greater than 0.05 and the other condition, then reject observer I. That's what it says. Okay, so if there's a consistent bias, an absolute bias, not with a sign, just an absolute bias, and if it's rated inconsistently above and below the MOS, then it's likely to be an outlier. And then they have these hard threshold, 0.05 and 0.3. And this is, I think, the problem here that you brought to the light. Namely, these numbers surely depend on the type of test that you do, the materials, and the context in which the study has been carried out. So if you change these numbers, you will get quite different conclusions. Maybe you will find that BT500 does not discard 100% of the people as outliers, or many of them as outliers, as you have found in one experiment here. So one solution to this problem is that you should not have such absolute thresholds, but rather come to an agreement saying, for example, let's say we have 100 participants and we just set the set of outliers, or the number of outliers, to be equal to 10. So 10% of our participants should be regarded or classified as outliers. If 10 is too high, if there's really only 5 outliers, 5 that really perform badly, then we discard 5 that are good. That's not such a bad thing, because we still have the other 90%. But it's really bad if we keep some outliers in there in the analysis. And so what we have done successfully in previous work is to be motivated by this BT500, change this a little bit in order to use this philosophy by saying, okay, we want to discard 10% of the users, or 5% or whatever it is, as outliers, and then just reject those participants that score the worst. So we have to combine the two criteria into one, and then use a threshold on that, or just discard or rank the users according to this scalar quantity, and discard the worst 10%. Okay, that's one comment, and the other comment that I have that I would like to suggest is regarding the problem that if you scramble one of the participants' ratings, so you artificially make that truly an outlier, it's just random, then this outlier may or may not be detected, but in any case, you expect that it has side effects, namely that some people that were not detected as outliers before now are outliers, and you showed this in your experiment. this is a sign that this outlier removal technique is not robust. The robustness is a technical term here. It means that the outliers, you have statistics that determine the outliers, and the statistics should, for a robust method, statistics that you use to determine the outliers should not depend on the outliers. But this is intrinsically a difficult problem, because whenever you have these hard thresholds here, then once you remove those outliers, the masses will be different, and so the statistics have changed. And the one solution out of this is to make this robust is to iterate this procedure. Once you have removed your outliers according to BT500 or P913, then recalculate your statistics from the good candidates that are still there, and then re-identify outliers from the whole set. And then iterate this, and you will find, maybe you'll be surprised, that this whole procedure converges, and at the end, the outliers do not affect the statistics anymore. And this can actually be proven, theoretically or mathematically in some contexts, maybe not in the context that is addressed directly here, but BT500. And so we have used this technique also of robust outlier detection in connection with the philosophy of BT500, not using their exact formulas, but similar ones. Mm-hmm. So these are our comments from our group here in Konstanz.
Yeah, thank you very much. So I will just answer then. I mean, if Lucian wants to add something, of course, he can. For the first comment, indeed, I mean, the sensitivity of the thresholds is something that we see for both methods, basically. And especially for BT500, what we saw and made us question, basically, whether the implementation was correct or not, when we saw that all of them were detected as outliers, it was exactly this. It was that the thresholds were a bit too strict on the matter. And basically what we saw when 100% of the outliers were detected was that out of 160 cases, 7 or 8 times one subject would rate either above or below, in total around 16 times they would rate differently, which is 10% of the cases. And that's why all of them were detected as outliers. But this is to be expected when we have such a tight distribution, which means that a small variation brings you outside of what the limits are decided. Now, we have been discussing about this topic of whether to use a threshold and then not put any hard numbers on the number of outliers. And we can detect 0 outliers, we can detect all of them, versus the fixing a number of outliers and just saying, okay, we remove this X number of worst cases, regardless of whether they were outliers or not. It's a very, it's something that I think the community hasn't agreed on. And well, the methods that have been used are usually trying not to fix the number of outliers, but just removing. But something good can be said about the method of just fixing a number of outliers and just saying, okay, we remove the worst one, the others is what we're left with. And if we remove some good scores, well, so be it, which I think was the spirit of your first comment. And I don't know if Lucian wants to add something about it.
Thank you for the comment. For sure, we will consider it for what is still something hard for me to accept is that a scrambled person is not detected. And then any method that is not detecting a scrambling results for me is simply wrong, because this happens. Yeah, this could happen to me, that within the subjective experiment, I did an error. Somehow the IDs of the movies are not correlated with the results, and then I have scrambled results, and I need to detect it because those are definitely useless. The people watch different video that they scored, and this is simply scrambling. So in my opinion, any method that is under consideration should detect a scrambled result, because this simply can happen.
Yeah. This brings back to the robustness comment, which is indeed one problem for BT500, in the sense that we saw that there was a high variability in the detected scramble, but also we saw that previous outliers were not detected, for example, after we scrambled, and the new outliers were found, which is a huge variability in the way that it's done. We also saw it in P913, although it was much better, in the sense that we saw, the only problem that we saw, that some previous outliers, considering this after the scrambling, were not detected as such. But this comes from this repetition. So the comment that you had about repeating the statistics iteratively, that's what P913 does, basically, in which it considers the correlation of each subject. It removes one subject and then repeats the correlation. If none of them is below the threshold, it just simply stops. So this we saw that there was some robustness issues in here, for which if a score with the 25 subject was very close to the threshold, so it was considered an outlier because it was right outside of the threshold area. Then if you remove one subject because you're scrambling it and then it's detected 100% of the time, so the subject is removed, then the next time maybe the correlation with 24 subjects, it is such that it's not detected anymore because it's brought a bit higher, but it was not the case before. We're not sure that this is a problem in itself of the method. It's just something that we observed. For BT500, iterating could be a very nice idea because it's not iterative as it is right now, but it's just computing them, considering all of the thing. And indeed, after detecting the one outlier, it would be nice to do the same procedure as P913 and doing the same iterative process and seeing whether the outlier is detected or not.
Thank you very much.
Thank you.
Thank you. Z, I see you have a question.
Yeah, I just wanted to use this opportunity to again raise the awareness of MLE-based approach. I think it's very much along the same line as here the investigation. So if you think upon a higher level, MLE is essentially, you can consider it as a rejection methods, right? So it's not that MLE doesn't reject subject. It's just like it rejects subjects in a different way. It's in a soft rejection. And a perfect analogy for this will be if you're familiar with K-means algorithm, right? Think of K-means as a hot thresholding, hot rejection kind of methods. The counterpart of the soft rejection will be expectation maximization, the EM algorithm, right? So it's well known that the K-means is a special case of the EM algorithm, right? But EM is more performant in the sense that it doesn't just simply throw away information. It takes into account all the information and be able to make a holistic decision. And same thing applies here to the MLE-based approach. It doesn't throw away information. And if the main interest here is about scrabbling, I would argue that MLE is actually doing very well in this particular scenario, right? So I would really encourage a thorough comparison of the MLE soft rejection-based method with BT500, P913 hot rejection methods. So one of the features for the MLE is, I think we talk a lot about this parameter selection, the difficulty of deciding on hot threshold used in those hot thresholding methods. And one of the beauty of the MLE-based approach is that you don't do any hard-coded parameter at all. So everything is being boils down into this. So you could essentially think it as adaptively selecting the weight, right, to decide how much you want to, instead of weighting something as a 0 or 1, right, you assign a weight based on the information at hand, right? So, so one more aspect I would also want to say is that we did a fairly thorough comparison of MLE versus BT500, P930, but we didn't try to change the threshold of BT500 or P913. But we run a comparison on our crowdsourcing data sets. We have seen that there is a big benefit of using the MLE to analyze crowdsourcing data sets. And there is a significant advantage using MLE-based methods. So I would really encourage the previous speaker who tried to use the BT500 also to try your crowdsourcing data on the MLE-based method. I could give you more pointers after this meeting. Thanks.
Thank you. No, indeed, we want, as Lucian said before, we also want to compare to MLE. It was more that the type of analysis that we're running here, in which is really like seeing whether the person was detected as an outlier or not, it is a hard method, so that's why we use the hard detection mechanism. But indeed, like the future work is also incorporating MLE and seeing how it performs in this type. And as I said, scrambling is only one way in which a person can be an outlier, and it's the most obvious, we would say, in the sense that it's really like it's a random assignment of scores. But we saw with BT500, I think we did the other test, like at a certain point, we really wanted to find out outliers with BT500. So we tried to put everything to 1 or everything to 5 or really flipping the scores, and still it wasn't detected as an outlier. So there is different ways in which one can tamper with the scores in order to see whether they are detected or not. And it would be interesting to see how different methods fare with this type of tampering. And it's for sure future work for us. But thank you, like, and we will really take into consideration MLE as well.
Thank you very much. Yeah, I like very much the discussion. Dilma, do you have another suggestion, or your hand is up since the question? Okay, I assume this is still up. Okay, thank you very much once more for the discussion. And now we can switch to the last topic, which is the future of SAM. And also discussing when we could have online meetings. As we can clearly see, the SAM meetings are super interesting for the community. We had a wonderful discussion. Yeah, I really like it very much. And I'm sure we still have some open issues. The one that was brought by C, I like very, very much. And we definitely want to develop more the directions and further analysis of the different subjective experiments and subjects analysis methods. So any thoughts? Yes, Margaret, please.
So I'm interested in better ways to understand similarities and differences between subjective tests conducted at 2 labs. And my motivation is not to understand subjective methods themselves, but to be able to have an improved way of saying what is the precision of objective metrics. So my proposed starting point is the analyses I presented last meeting about confidence intervals and using a confusion matrix to understand the difference between subjective tests at 2 labs. But I'd also like to explore what other ideas people have in addition to what people think of those methods.
Thank you very much. Yeah, this is definitely a very important part of the analysis, that we are not only focusing on subjects themselves, but also including the metrics and analysis of the metrics. Any other thoughts? Please.
Yeah, I just want to bring up a topic that we have a pretty strong interest in, but we never got a chance to fully explore, which is considering like moving test over to the crowdsourcing platform, the kind of challenges we need to address to make the data, the results more reliable. And also like being able to operate in a cost-effective manner. Along this direction, I've been thinking things like active sampling, where the selection of the condition, the stimuli to be tested on the subject is based on the fly online analysis of what you already have collected so far, right? I think we're still kind of lacking in this perspective. this is partly motivated by this COVID. We expect it will still be going on for quite a bit. And even after the COVID, I would say that there is going to be a long-term impact if we will be able to have more intellectual contribution to this field. I think it's going to be a very, very promising.
This is an excellent idea. Very interesting for sure. So as we can see, we definitely have some ideas and thoughts for some. From the AGH side, we will definitely bring the new ideas with a different distribution than the one that is based on normal distribution. We already presented a couple of things with generalized score distribution. But hopefully, in the next months, we could develop this idea further, and also speed up the estimation process, which already was done, and also bring it more into the estimation based on the whole experiment. Until now, we were focusing on a single PVS estimation. Now we are slowly moving into the multiple. Or the whole experiment estimation, similar as the MLE method for the normal distribution. Ioannis, please.
I would like to express our real interest to. Hold on just a second. Sorry about that. Can you hear me?
Yes.
Yeah. So as I was saying, we would like to express our interest in both of the items brought up, both by Margaret and by Z. We think that exploring other distributions is actually also a very good solution. So we are keen to join these efforts and contribute resources to make it happen. And apart from that, I think that some of the items that brought up during this call, for example, the ability to classify subjects into potential clusters, whenever that is the case, in a systematic way. So in other words, do a statistical analysis that would be able to extract those clusters would also be of importance to us. And that will depend, of course, on the experiment and whatever other conditions we can do, either on the HRCs or the viewing conditions or anything else. So we'd like to explore, let me say the word context, that could differentiate certain subjects from others. Thank you.
Thank you very much. Yeah, sorry for small disturbance. Literally small. Okay, so definitely we want to sit further. We see a lot of interesting topics for some. So in my opinion, it's kind of obvious that we would like to continue with discussion. And I think this idea of having once 4 weeks having a meeting, this is something that we would definitely want to come back. Is it correct? Yeah, I see the from C, and I guess. Thank you. So now the question is, what is the good time spot for that? And any thoughts about any strong opinions, or we'll just come back to the old ones?
I would like to keep the same Monday at the same time of day we had, because I've organized all of my other meetings to leave that as an empty spot for this effort. And for the norm meetings, I've been squeezing in between.
Yeah, perfect. I think that this is the most logical solution. So let us come back with the some meetings actually after this meeting. Can you create a calendar event? Thank you very much. Yeah, I'm very appreciate. All right. So this is the end of the SAM session. I think it was really interesting with lots of discussions and ideas for the future work. And if you have any thoughts, just please contact us. definitely you can send an email to our mailing list and also join our each 4 weeks meetings. And the next one should be in 4 weeks, I guess. Is it correct? See? Yeah.
Should I put the next one to be after the new year? Which week do you prefer to have the new commencement meeting?
Z, I'm fine starting on the 10th. Could you send me an email directly with the information that should go on the main VQEG webpage? Like listing
Sure.
the first 3 meetings?
Okay, so let's decide if we go is the 10th. Yes. Sounds good. If no objections, I will just put up for the next meeting to be on the 10th of the January. Does that sound good to everybody?
Yeah. Doesn't fit perfect my schedule, but I will fit to the others. I do my best to do it. Okay. Thank you very much. And I give the floor back to the chairs if anyone wants to add something.
Okay.
Hearing none, thank you very much.
Yes, thank you very much for an interesting and productive day. Before we close, I would like to go through the meeting minutes. So I'm going to share that. And come on. Okay, can people see my screen?
Yes.
Yes.
Okay. So we start with summaries of at the beginning, ADHD. I'm going to go down through these relatively quickly, through these summaries. Thank you to whoever inserted web page links and other notes. QAH, Sam, recall this urgent notice on the quality assessment for health applications. On CGI, we have a note. Okay, so for future consideration, we should use the heading style in minutes. If anyone is willing to go back and correct that, it would be nice. Norm and IG VQM, the implementer's guide. JIG hybrid, joint work going on. Kakovia, there was no summary. GKPI, Immersive Media Group. I think we should probably highlight these. The meetings. Immersive Media Group. Is it light field? Is that the correct term here? Okay, since there's nobody online who knows the right answer, we'll leave it as is. There's the Qualinet tools and human factors.
Yes, it is light field. There is a typo. It is not life-based, it is light field.
Okay.
Thank you.
Thank you. On JIG hybrid, presentation 214, updates on activities. pointing out to results in a previously published paper. 215, AI observers. And presenting those 3 subtopics summarized. I would like to remind presenters, please email me your slides so I can make them available. And as per the email I just sent out, I put file names in the presentation web page. There's the link there to answer Lohik's paper. On SAM, the tale of 2 data sets. Boer has the link to the paper describing the method and the link to the data set. And here I tried to capture some of the discussions we had. And note there's a call to other labs to repeat the fuller method. Presentation 225 on the new subject removal method. Again, noting some of the results and future area for future research. On the future of SAM, Lutin, I was not able to get all of your proposal there. Could you add some text here? Or
no, different distributions. Okay, but this is okay. So it can be all collapsed to working on generalized score distribution. No, thank you very much.
Okay. And Z, likewise, could you check over my summary of what you said?
I believe Z is not on the call anymore.
Okay. Well, we will leave it as is then. And it should be. So we agreed to have audio calls every 4 weeks, starting January 10th. Okay, are there any other changes to the minutes? Hearing none, I will mark these minutes as approved, and we will officially close the VQEG meeting for today. Thank you very much, everyone, for participating, and I look forward to an interesting and long day of discussions on no reference metrics tomorrow. Thank you, Femi.